Welcome to the SAR channel, where sound and audio are demystified. Digital audio systems work very differently from analog ones. Since sound is naturally analog, digital systems convert it into a digital form using two main processes, sampling and quantization. Sampling involves measuring the sound at regular intervals, while quantization converts these measurements into a digital number. According to the sampling theorem, the sound must be limited to a certain range of frequencies for the sampling to work correctly. If not done properly, a problem called aliasing can occur. Quantization error happens when the digital system doesn't perfectly match the analog waveform, but this can be reduced by a technique called dithering, which helps smooth out the error before converting the sound. In analog recording, sound is recorded continuously, like a tape being modulated or a groove being cut. In digital recording, however, sound is represented by discrete numbers. These numbers are created using two key processes: temporal sampling, measuring sound at specific moments, and amplitude quantization, turning those measurements into digital values. Time seems to flow continuously, like the hands of an analog clock moving smoothly. But a digital clock shows time in discrete steps, just like digital audio samples time in separate, individual points. Music, like time, changes continuously, but it can be recorded and played back either continuously, analog, or discretely, digital. Discrete time sampling is what makes digital audio systems work, allowing them to convert analog sound into digital form and making them different from analog systems. Now you might wonder, if digital systems only capture sound at specific points in time, does that mean we lose information between those points? The answer is no. If the system is set up correctly, no information is lost. The discrete samples can still represent the entire audio signal accurately. Think of a video camera connected to a car. The camera records images in discrete frames, but when watching the video, the images seem continuous. However, if the car moves too quickly or the road is too bumpy, the video may blur because the frames can't capture all the movement. To fix this, we'd increase the frame rate, taking more frames per second to capture the fast changes. This analogy isn't perfect. A movie is a series of still images, and it's our brain that makes it look smooth. But it helps explain how digital audio works. Just like the frames in a movie create a moving image, digital samples create a continuous sound when played back. For this to work properly, the signal needs to be prepared before sampling. High-frequency noise must be removed with a low-pass filter so that only the frequencies that can be sampled accurately are recorded. If done right, the digital system captures all the necessary information, and the original sound can be fully reconstructed from the samples. The sampling theorem explains that a continuous signal with a limited range of frequencies can be converted into a series of discrete samples without losing any information as long as the right conditions are met. Specifically, the signal must be sampled at a rate that is at least twice as fast as its highest frequency. For example, an audio signal with frequencies between 0 and s over 2 Hz can be perfectly captured using s samples per second. This means the sampling rate needs to be at least double the highest frequency of the signal being recorded. The sampling theorem is often credited to Claude Shannon, a mathematician, or Harry Nyquist, an engineer. The maximum frequency that can be correctly sampled is known as the Nyquist frequency, which is half of the sampling rate. When audio signals are sampled, they first pass through a low-pass filter that removes frequencies higher than the Nyquist frequency, s over 2. This means only the frequencies below half the sampling rate are kept. Ideally, this filter removes only those high frequencies beyond human hearing. Once filtered, the signal can be safely sampled, capturing its amplitude at specific moments. The sampled signal contains the same information as the filtered original, and when it's reconstructed, no information is lost. The output signal is an exact recreation of the input band-limited signal. The sampling rate determines how often samples are taken. For example, a rate of 48,000 samples per second means one sample is taken every one divided by 48,000 of a second. High-frequency signals, which change rapidly, need higher sampling rates. Therefore, the chosen sampling frequency sets the system's maximum frequency limit and overall audio bandwidth, making it a key design factor. According to the sampling theorem, to capture a signal accurately, the sampling rate must be at least twice the highest frequency present. So, to record audio up to 24 kHz, a sampling rate of 48 kHz is required. If frequencies higher than the Nyquist frequency enter the system, they cause aliasing, distortion. To prevent this, a low-pass filter is applied before sampling, and another one at the system's output to remove unwanted high frequencies, ensuring the original waveform is properly reconstructed. Using higher sampling rates allows recording higher frequencies, but it doesn't improve sound quality for signals that already fall within a lower frequency range. Sampling points don't always line up with the waveform's peaks or zero crossings, but this doesn't affect accuracy. Since filters can't perfectly block all frequencies at the Nyquist limit, a guard band, a small margin below it, is used to ensure no unwanted frequencies enter the sampler. In practice, there are always more than 2 samples per waveform cycle, though the samples aren't perfectly in phase with the waveform. The final reconstructed signal is built from the combined responses of many samples, not just individual points. Because all audio signals have finite bandwidth, both analog and digital versions can represent the same information. Higher sampling rates require faster circuits and more data handling, which increases cost and complexity. For example, CDs use 44.1 kHz to balance quality, cost, and storage time, while DVD audio and Blu-ray can go up to 192 kHz. In essence, the sampling theorem shows that a band-limited signal can be sampled, stored, transmitted, and perfectly reconstructed without losing information, proving that the output waveform can be identical to the original. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. Let's continue. Aliasing is a type of distortion that happens during the recording or sampling of a signal. It creates false frequencies, spurious signals, that can fall within the audible range and sound just like real audio, making them impossible to separate from the true signal. Preventing aliasing is a key part of system design. Sampling itself can be lossless if done correctly. To ensure this, the input signal must first be filtered using a low-pass filter to remove frequencies above the Nyquist limit. If not, the system will undersample the signal. A common visual example is when a car's wheels in a movie appear to slow down or spin backward. This happens because a camera recording at 24 frames per second can't capture the fast movement of the spokes, a clear case of aliasing. Aliasing occurs when the sampling theorem is violated, meaning the signal contains frequencies higher than the Nyquist frequency, half the sampling rate. When frequencies go beyond this limit, there aren't enough samples per cycle to represent them correctly. At the Nyquist point, there are exactly 2 samples per cycle, the minimum needed. Above this, the samples begin producing false, lower frequencies known as aliasing frequencies. These appear as if higher frequencies have been folded back into the audible range, a process often called foldover. For a simple sine wave, aliasing only affects part of the waveform, but for complex sounds containing many frequencies, aliasing can affect all parts of the spectrum above the Nyquist limit, causing noticeable distortion. In a well-designed digital system, aliasing is prevented by using an anti-aliasing filter before sampling. This low-pass filter sharply reduces frequencies near the Nyquist limit so that no unwanted high-frequency content enters the digitizer. Ideally, the filter has a very steep brick wall cutoff that completely blocks frequencies beyond the desired range. It's essential to follow the sampling theorem and apply proper filtering to avoid aliasing. Once aliasing occurs, it cannot be removed. The false frequencies permanently contaminate the recorded audio. For any changing signal to be meaningful, both when it's measured and what value it has must be recorded. In audio, sampling captures the timing of the measurement, while quantization captures the amplitude, loudness of the waveform at that moment. Together, sampling and quantization describe an audio signal digitally. Sampling controls the bandwidth, and quantization controls the resolution. An analog waveform can be represented by a series of pulses, each with an amplitude value. Quantization assigns a numerical value to each pulse to represent the waveform's level at that instant. However, this process isn't perfectly accurate because digital systems have limited resolution. Since only a fixed number of levels can be used, a small error is introduced. This error behaves like background noise in analog audio, though it can sound worse because it changes with the signal's loudness. In uniform quantization, the continuous range of analog amplitudes is divided into a finite number of equal steps. Every sample's amplitude must be rounded to the nearest available level, creating a small inaccuracy. The more quantization levels there are, the higher the sound quality. For example, a high-quality recording might use 65,536 amplitude levels or more. These levels form the basis of pulse code modulation, PCM, which is how digital audio carries information. In analog systems, measurement errors come from mechanical or electrical noise in the device. In digital systems, accuracy depends on the number of bits used to represent each sample. More bits mean finer resolution and better accuracy. The last digit, however, must still be rounded from the actual value. Both analog and digital measurements face limits, but digital readings are generally more precise and stable. Quantization is the process of turning an analog sound into numbers using a binary system. The number of bits used, the bit depth, determines how detailed the representation is. For instance, 16-bit or 24-bit quantization defines how finely the signal's amplitude can be measured. The actual accuracy also depends on the quality of the analog to digital AD converter. Although sampling itself can be theoretically perfect, quantization cannot be, because an analog signal has infinite amplitude values, but a digital signal has finite amplitude values. System can only represent a finite number. Every analog value must be rounded to the nearest quantization level, making the digital result only an approximation of the original waveform. The more bits a digital system uses, the more accurately it can represent the original analog signal. However, some quantization error always exists because a limited number of digital levels can never perfectly match the infinite range of analog amplitudes. Creating a high-quality digital audio system means keeping this error as low as possible, which is technically challenging. When the quantization error becomes small enough, it becomes inaudible. Most experts agree that 16 to 20 bits provide good quality sound, though higher resolutions can further reduce error. Some systems like DVD and Blu-ray use 24-bit words, and many digital recorders apply noise shaping to minimize the audible effects of quantization noise within the audio range. The word length or bit depth defines the resolution of a digital system and is key to evaluating its quality. Sometimes the analog signal fits perfectly within a quantization level, but usually it doesn't. In the worst case, the analog value falls exactly between two levels, creating an error equal to half of the smallest quantization step, half of the least significant bit, or LSB. Quantization error is simply the difference between the true analog amplitude and the quantized digital value. Each time the signal is sampled, its amplitude is rounded to the nearest step. If the analog value lies between two steps, the quantizer must choose one, creating a small error. This happens for every sample in the system. The size of this error is never greater than half an LSB. The resulting distortion exists at all signal levels. When the signal is loud, the distortion is small and usually masked. When the signal is quiet, the distortion becomes more noticeable. To measure a digital system's performance, we use the signal-to-error ratio S/E, the ratio between the largest possible signal level and the largest possible quantization error. This ratio is similar to the signal-to-noise ratio used in analog systems. Each additional bit in word length increases the signal-to-error ratio by about 6 decibels, or roughly doubles it. This happens because every extra bit doubles the number of quantization levels, which cuts the spacing between levels in half, and therefore halves the quantization error. If you have learned anything new so far, please like the video. It really helps the channel grow. Thank you. When analyzing quantization error in quiet or low-level signals, it becomes clear that the error depends on the original signal itself. This means it's not the same as random noise. When the digital samples are converted back into an analog waveform, some of this error shows up within the audible range. Because the error changes with the signal, it's considered a form of distortion, not noise. The size of the error depends on the spacing between quantization levels. More levels mean smaller errors and less distortion. The issue becomes worse as the signal's amplitude decreases. A very quiet signal might be represented by only one bit or might not register properly at all. As signal level drops, the percentage of distortion increases. For example, distortion is minimal at full scale, 0 decibels fs, but rises sharply at low levels like -90 decibels fs. To minimize this problem, engineers use a technique called dithering. Unlike the noise floor in analog systems, the error floor in digital audio depends on the signal itself. The behavior of quantization error changes with both the loudness and the complexity of the sound. For strong, wideband signals, the error tends to resemble white noise, and each sample's error appears random, making it less noticeable. In this case, the error acts much like analog noise, except that digital error values are evenly distributed between positive and negative peaks, while analog noise often has higher peaks than its average level. However, predicting how quantization error will sound is difficult because it depends on the signal's randomness. In high-level, complex signals, the correlation between samples is low, so distortion is minimal. But for quiet or narrowband sounds, the correlation increases, making the error more structured and harmonically related to the signal. This produces harmonic and intermodulation distortions, as well as modulation that changes with the noise floor. Quantization distortion can take many forms, sometimes even creating frequencies above the Nyquist limit, leading to aliasing. For example, in a system sampling at 48 kHz with a 24 kHz bandwidth, a 5 kHz sine wave that's only one quantization step high will be turned into a 5 kHz square wave. This generates harmonics at 15, 25, and 35 kHz, which fold back, alias, into the audible range at 23 and 13 kHz. Other harmonics and aliases also appear. This aliasing from quantization can cause a rough, gritty-sounding noise known as granular noise. In loud sounds, it's masked by the main signal, but in quiet sounds it becomes audible and unpleasant. If aliasing frequencies align closely with multiples of the sampling frequency, they can even create rhythmic or chirping tones called bird singing. As a sound fades out, its waveform passes through fewer quantization levels, causing the noise to shift from smooth white noise to distinct distortion tones. This is especially noticeable because most sounds become more sinusoidal as they decay, and their fading amplitude modulates the distortion. To solve these issues, engineers use Dither, a small amount of added noise, which helps make quantization distortion less audible and more natural. Quantization isn't only about bit depth, it also depends on how the hardware is designed. There are different ways to assign quantization levels to analog signals. For instance, a quantizer can divide the amplitude scale into equal linear or unequal nonlinear intervals. Another method is delta modulation, which uses one bit to represent amplitude and another bit to show whether the signal is increasing or decreasing. Some systems use oversampling and noise shaping to push quantization noise outside the audible range. These design choices affect both how efficiently the bits are used and how noticeable the noise is. For example, a linear quantizer causes more error in quiet sounds that use only a few levels. A nonlinear system with floating point conversion boosts the level of quiet sounds so they use more of the available range. This improves the signal-to-error ratio, but it can also cause unwanted noise modulation. After weighing these pros and cons, manufacturers decided that linear fixed quantization works best for music recording. Still, low bitrate formats like DSD challenge this view. In complex, loud signals, the quantization error is mostly random and sounds like analog white noise. But in quiet signals, the error becomes linked to the signal itself, which can cause audible distortion. A good digital system must hide or eliminate this distortion. One way is to increase bit depth. Each added bit reduces error by 6 decibels, but this quickly becomes inefficient and still doesn't solve the problem for very low-level signals. Dithering offers a better solution. Dither is a tiny amount of random noise added to the signal before sampling. This makes the quantization process more linear by breaking the pattern between the signal and the quantization error. As a result, the error becomes random and less audible. Although dithering adds a small amount of noise, it greatly reduces distortion. When done properly, the number of bits sets the overall noise floor but does not limit low-level detail. Signals as quiet as -120 decibels fs can still be detected in a dithered 16-bit recording. Quantization works like a hard limiter, creating distortion when not handled correctly. Dither smooths this by allowing the quantized signal to follow the average of the input. This creates a pulse-width modulated PWM pattern that preserves fine details below the least significant bit, LSB. The ear, which naturally averages sound, hears this as a clean tone with soft noise instead of a harsh square wave. With dither, quantization error becomes random, zero mean noise, instead of signal-dependent. In non-subtractive dithering, this noise is permanently added to the audio. In subtractive dithering, the dither is removed after processing, which reduces total error even more, but is harder to implement. Dither makes it possible to represent details smaller than one quantization step. For example, quantizing a 1 kHz sine wave only 1 LSB tall would normally produce a square wave, but with dither, the quantized output becomes PWM, carrying the sine wave's information within the varying pulse widths. The ear perceives this as a low-noise sine tone rather than distortion. Although dither raises the noise floor slightly, this effect is minor compared to the huge signal-to-error ratio in digital audio and can be shaped to be less audible. High-frequency dither signals, placed below the Nyquist frequency and above hearing range, can further reduce perceived noise. In short, dithering reduces digital distortion and rounding errors, and even small amounts can make a digital system sound more natural and analog. Sampling and quantization are the two main processes in turning sound into digital form. The sampling rate controls the range of frequencies that can be captured, while ignoring the sampling theorem can cause aliasing. Quantization sets the system's dynamic range, expressed as the signal-to-error ratio. Sampling itself doesn't lose information if done correctly, but quantization is always an approximation that can introduce errors. These quantization artifacts can harm sound quality, yet adding dither can remove distortion and keep the recording faithful to the original sound. In practice, sampling rates of 44.1 or 48 kHz with a dithered 16 to 20-bit depth deliver clarity and precision equal to or better than the best analog systems, while also offering longer life and more accurate playback. Even higher resolutions like 192 kHz with 24 bits can achieve superior performance. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.